Welcome back to AI.Code.Cast. You know, we'd love to dig into a new coding challenge every day, and today's problem is really going to make you think. It's called maximum sum of distinct subarrays with length k. So,
It's a good one.
basically, you get this array of numbers, and you have to find a subarray, which is like,
A chunk of consecutive numbers.
right, a chunk within that array.
Yeah.
But there's a catch. There are two specific rules it has to follow.
Two criteria. Yeah.
So first, you need to find a subarray with a length of k.
K is a specific size that's given to you in the problem.
Right, k is like the target length.
Mm-hmm.
But here's the twist. All the numbers in that subarray, they got to be unique.
Absolutely no repeats allowed.
So it's not just about finding any subarray of length k. It has to have all different numbers. And then on top of that,
You want to maximize the sum.
you got it. The goal is to find the subarray with the highest possible sum. This is where it gets really interesting, right?
Yeah, definitely. This problem really gets you thinking about algorithms and how to make your solution as efficient as possible.
It's like being a detective. You have all these clues, the numbers in the array,
And you need to find the right combination.
to unlock the case, yeah.
Yeah,
The subarray with the maximum sum.
exactly.
Okay, so let's say we get hit with this problem in a coding interview. Where do we even begin? I mean, there's always the brute force method, but that doesn't seem very clever, does it?
It's rarely the most efficient way.
It's kind of like
Trying every key on a giant key ring.
until you find the one that opens the door.
Right. It's not very elegant, but it's a good place to start, just to wrap your head around the problem.
So how would that brute force approach actually work for this problem?
Okay, well, imagine this. You go through every single possible subarray in the given array.
Every single one.
Yeah, you have to be thorough. And for each subarray,
You're checking if it's the right length, right?
exactly, you got to make sure it has length k.
That's our first rule.
And then you go through all the elements in that subarray,
One by one.
one by one, making absolutely sure that you haven't seen that same number before within that subarray.
Like if you find a duplicate.
That subarray is out. It's disqualified.
Okay, so let's say we have a subarray that passes both of our tests.
The right length and all the numbers are unique.
Then we calculate its sum, and we're basically keeping track of the highest sum we come across.
Exactly. You're looking for the champion?
The champion sum, yeah. But wouldn't that take ages? Especially if the array is huge?
You're hitting on a key point here. The brute force approach can be really slow, especially as the array gets bigger. The time complexity, which is how we measure efficiency in computer science.
Yeah, I remember that from my algorithms class.
It's ON2 for brute force.
Meaning?
It means that the time it takes to run your code increases quadratically with the number of elements in your array.
So if you have like 1,000,000 numbers in your array.
This method could take forever. It's not really practical for large data sets.
Okay, I get it. Brute force is kind of a no-go if we want to be efficient. But before we jump into a better solution,
Sure.
I think it's good to clear up a few things. Some questions that might pop up.
Yeah, let's do it.
What happens if there's no subarray of length k that has all unique elements?
Ah, a classic edge case. In that case, we simply return 0.
Yeah.
0.
Yep, zero. It's like saying, we looked everywhere, but there's no treasure here.
So we're signaling that we couldn't find a subarray that follows the rules.
Precisely.
Okay, that makes sense. What if k is bigger than the length of the whole array?
Another good one. So if k is bigger than the array itself, well, you can't exactly find a subarray of that length, can you?
It's like trying to fit a square peg in a round hole.
Exactly. So again, we'd return 0. We just can't find what we're looking for.
Okay, last question. What about negative numbers? Are those allowed in our array?
Absolutely. The numbers can be positive, negative, or even 0.
Our goal is still the same though, right?
Of course. We still want to find that subarray of length k with unique elements that has the highest sum.
Even if that sum happens to be negative.
Exactly.
Yeah.
You got it. Okay. Those edge cases are crystal clear. Thanks for clearing that up. Now, I know there have to be a better way to solve this problem. Something more elegant than trying every single key on a giant keyring.
You're right, there is. There's a technique called the sliding window.
Sliding window. What's that all about?
It's a really cool way to solve problems that involve looking at consecutive chunks of data.
Chunks, like our subarrays.
Yeah, exactly. Imagine you have a window.
Like a real window.
Yeah, kind of. It's sliding across our array. The window always covers k elements at a time.
K being our target length.
Right, and as the window moves, we analyze the stuff inside it.
So instead of looking at every possible subarray.
We're focusing on these sliding chunks of k elements. Much more efficient.
That's smart. But we still need to keep track of whether all the elements within that window are unique, right?
You're absolutely right. That's a critical part. We need a way to quickly know if we've seen a particular number before within the current window.
What if we use a dictionary? Or a hash map, as some people call it.
Ooh, I like where you're going with this.
We could store each element as a key.
And the value for each key?
Could be how many times we've seen that element within the window.
You're on fire. So if we come across an element that's already in our dictionary,
We have a duplicate.
you got it. We've got a problem.
Okay, I think I'm starting to see the pieces fall into place here. Let's try to break this sliding window solution down, step by step. First, what are the variables we need to set up at the beginning?
All right, so first off, we definitely need a variable to remember the best solution we've found so far.
The highest sum we've seen for a valid subarray.
Exactly. Let's call it maxim.
Maxim. Okay, what else?
We'll also need a variable to hold the sum of the elements in our current window.
So we can keep track of the sum as the window slides along.
You got it. We can call this one current sum.
Makes sense.
Yeah.
So we have maxim and current sum. What about the window itself? How do we keep track of where it is in the array?
Ah, great point. We need something to mark the beginning and end of our sliding window.
How about a left pointer for the start?
Perfect. And of course, we'll need a right pointer to mark the end of the window.
Right. So now we have our maxim, current sum, our left pointer, and our right pointer. And let's not forget,
Our trusty dictionary to keep track of element counts.
which we called element counts, right?
You got it. We'll use that to efficiently check for duplicates within the window.
Okay, so we have all our variables set up, maxim, current sum, left, right, and element counts.
Yeah.
Now, how do we actually make this window slide across the array?
All right, so think about how a real window slides. We're going to move the right pointer one element at a time.
So we're expanding the window to the right.
Exactly. And with each step, we add the new element, the one the right pointer's pointing to our current sum.
So we're adding the new element to the running total.
Precisely. But remember, we also need to check for those duplicates.
That's where our element counts dictionary comes in handy, right?
Exactly.
Yeah.
Every time we add an element to our window, we need to update its count in the dictionary. So if that element is already in the dictionary,
Hold on. If it's already there, that means
we've found a duplicate.
a duplicate in our window
And that breaks our rule. So we need a way to shrink the window from the left side.
until that duplicate is gone.
Exactly. We want to keep only unique elements inside our window.
Okay, so to shrink the window, we use a while loop, right?
You got it. As long as the element at the right pointer,
The one we just added.
yes. As long as that's still in our dictionary, we keep shrinking.
So we remove the element at the left pointer
From both the current sum.
and from our element counts dictionary. It's like we're pushing the window forward, getting rid of that duplicate.
And of course, we need to move the left pointer one step to the right as well, since our window has shrunk.
Gotcha. So we've added the new element, removed any duplicates, and updated our current sum and our dictionary. What's next?
Now, the exciting part. We need to check if this current window, with all its unique elements...
Is the new best solution?
Exactly. Is it a contender for our maxim?
But first, we need to make sure our window is the right size, right?
Of course. It has to have a length of k.
How do we check that?
Simple. We calculate the window size, which is just the right pointer minus the left pointer plus 1.
Plus 1.
Because we're dealing with array indices, which start at 0.
Ah, right. So if the window size is equal to k,
We know we have a window that's the right size.
and we know it only has unique elements because we just took care of all the duplicates.
Exactly.
So in that case,
We compare the current sum to our current maxim.
and if it's bigger,
We update the maxim. We found a new champion.
makes sense. And then,
And then we move our right pointer one step to the right, sliding the window over, and we repeat the whole process.
we keep going until the right pointer reaches the end of the array.
You got it. It's like a smooth gliding motion across the data.
Wow, this is amazing.
Yeah.
We went from that brute force approach, which was like trying every key on a giant key
To
ring.
this elegant sliding window solution.
It's so much more efficient.
It really highlights the power of choosing the right algorithm for the job.
Now, I'm really curious to see how this sliding window solution works in action. Can we walk through a specific example to see it in practice?
Absolutely. I think that's a great idea. It'll help us solidify our understanding. We'll dive into a concrete example right after this. Welcome back to AI.Code.Cast. We left off talking about this sliding window technique and how it's a much more efficient way to solve this maximum sum of distinct subarrays problem.
Yeah, it feels way more clever than just brute forcing it.
Right. So to really see how it works, I think it's helpful to walk through a specific example.
Yeah, let's do that. Let's see it in action.
Okay, so let's say our input array is 1, 4, 2, 3, 5, 4.
Okay.
And K, our target subarray length, is 3. So we want to find the subarray of length 3 that has the maximum sum with all unique elements.
Got it. So how does the sliding window come into play here?
Imagine our window is at the very beginning of the array.
So it's covering the first three elements, 1, 4, and 2.
Not quite. Remember, the window starts off small and expands.
Oh, right. So at the very beginning.
Our left pointer, which marks the start of the window, is at index 0.
Right.
And our right pointer, which marks the end of the window, is also at index 0.
So the window is just one element wide at the start.
Exactly. It's just covering the first element, which is 1.
And our current sum would be 1 as well, right?
You got it.
What about our element counts dictionary?
Ah, good catch. So at this point, our dictionary would have one entry. 1.
Meaning we've seen the number 1 once within the window.
Exactly. Now we need to expand our window. So we move the right pointer one step to the right.
So now it's at index 1.
Yep, pointing to the number 4.
Okay. What happens next?
We add the new element, which is 4, to our current sum.
So our current sum becomes 5, 1 plus 4.
Exactly. And we update our dictionary to reflect this new element.
So now it's 1, 1, 4, 1.
You got it. We've seen both 1 and 4 once within our window.
But our window is still not the right size, is it?
Nope, our target window size is 3, and we only have 2 elements.
So we keep moving the right pointer.
Exactly.
Okay, so now the right pointer moves to index 2.
Which is pointing to the number 2.
Right, so we add 2 to our current sum.
Making it 7, 5 plus 2.
And our dictionary becomes 1, 1, 4, 1, 2.
Perfect. Now we have all 3 elements in our window.
A window size 3.
And all the elements are unique.
So this is a valid subarray.
Exactly. So what do?
We need to compare our current sum to our maxim.
And since this is the first valid subarray we found...
Our current sum, which is 7, becomes our new maxim.
Exactly. We found our first potential maximum sum, but we're not done yet. We need to keep sliding that window.
So the right pointer moves again.
Yep, one step further to index 3.
Okay, now what?
So the new element at index 3 is 3.
We add it to the current sum, which becomes 10.
7 plus 3, that's right. And we update our dictionary. 1, 1, 4, 1, 2, 1, 3.
But wait a second. Our window size is now 4.
You're right. It's bigger than our target K, which is 3.
So what do?
Time to shrink the window from the left side.
So we move the left pointer.
Exactly, one step to the right. So it's now at index 1.
And we remove the element at index 0.
Which is 1.
From both the current sum and the dictionary.
You got it. So our current sum becomes 9, 10, 1.
And our dictionary is now 4, 1, 2, 1, 3.
Perfect. Our window is back to size 3.
And it still has all unique elements.
So we compare our new current sum, which is 9,
to our current maxim, which is 7.
And since 9 is bigger,
we update our maxim to 9.
You're getting it. We're constantly keeping track of the best solution we've found so far.
This is so cool. It's like we're reusing the information from the previous subarray. We don't have to start from scratch every time.
Exactly. That's the beauty of the sliding window technique.
So we keep sliding the window, adding new elements, removing old ones, updating our sum, and checking for duplicates.
And at every step we ask ourselves, is this the new maximum sum?
I think I'm getting the hang of this.
Yeah.
Now let's say we keep going and we reach a point where the right pointer is at index 5.
So it's pointing to the last element in our array, which is 4.
And we add it to our window. But hold on, we've already seen a 4 before.
Uh-oh. We have a duplicate.
What happens now?
Time to shrink that window again. We got to get rid of the duplicate.
Okay, so we move the left pointer to the right. It goes to index 2, and we remove the 4 at index 1 from the current sum in the dictionary. But wait, there's still another 4 in the window, the one at index 5?
Ah, good observation. This is why we need that while loop to keep shrinking the window as long as that duplicate element is still present.
So we keep moving the left pointer.
Exactly. It moves to index 3, and we remove the element at index 2, which is 2, from our current sum and the dictionary.
Okay.
And finally, the left pointer moves to index 4, and we remove the element at index 3, which is 3, from the current sum in the dictionary.
So now our window only contains the elements 5 and 4.
And we're free of duplicates.
Amazing. So we continue sliding the window until the right pointer reaches the end of the array.
And at each step, we repeat that same process. Adding the new element, checking for duplicates, shrinking if needed, and updating our maxim.
And by the end,
our maxim variable will hold the maximum sum of any subarray of length k that has only distinct elements.
Wow, this walkthrough has been so helpful.
Yeah.
I can really visualize how that window slides across the array and how we efficiently process everything.
I'm glad it's making sense. It's a powerful technique, and I think seeing it in action really clarifies how it works.
It does. Now, I know we talked about how this sliding window approach is more efficient than brute force,
Mhm.
but can we quantify that? Like,
Yeah.
how much faster is it?
Welcome back to AI.Code.Cast. So we just walked through an example of this maximum sum of distinct subarrays problem using a sliding window.
Yeah, that was awesome. I feel like
Great.
I really get it now. It's amazing how efficient that approach is compared to brute force.
Exactly. And that's what we're going to dig into now, the efficiency of these two approaches.
Okay, so we know sliding window is faster,
Hmm.
but can we put some numbers to that? Like, how much faster are we talking?
Let's break it down. So with brute force, remember, we have to check every single possible subarray.
Yeah, and that can be a lot of subarrays.
Right. And as we discussed earlier, that gives us a time complexity of O and 2.
O and 2, meaning
It means that the time it takes to run your code grows quadratically with the size of your input array. So if you double the size of the array,
the time it takes could quadruple.
exactly, it can get out of hand really quickly, especially if you're working with large data sets.
That makes sense. So what about the sliding window approach?
The sliding window is much more efficient because we're reusing information from previous subarrays. We don't have to start from scratch each time.
Right, like we saw in that example.
And this cleverness gives us a time complexity of ONN.
ON, linear time.
Exactly. So if you double the size of the array, the time it takes to run roughly doubles, much more manageable.
Wow, that's a huge difference.
It is. For very large arrays, the sliding window solution could be hundreds or even thousands of times faster.
Okay, so sliding window is the clear winner in terms of efficiency. But before we crown it the champion,
What's up?
we got to make sure it can handle those edge cases we talked about earlier.
The edge cases always got to be prepared for those.
So let's revisit them and see how the sliding window approach handles each one.
Sounds good.
First up, what happens if we have an empty array? Like, what if there are no elements at all?
Good question. In that case, our sliding window would have nothing to slide across. But don't worry, our algorithm is designed to handle this gracefully.
Gracefully. So it won't just crash.
Exactly. Since there are no subarrays to consider, our maxim would just stay at its initial value, which is 0.
It's like trying to find the biggest slice of a cake that doesn't exist.
Perfect analogy.
Okay, what about the case where k, our target length, is bigger than the entire length of the array?
Another good one. If k is bigger than the array, well, we can't possibly find a subray of that length.
Right, it just doesn't exist.
So in that case, our window would never be able to reach the size k, and our algorithm would again return 0. It's like trying to fit a square peg in a round hole.
I'm starting to see a pattern here return 0 if we can't find a valid subarray.
Exactly. It's a clear signal that something's not quite right with the input.
What about the case where there's no subarray of length k that has all unique elements?
Ugh, this one's a bit trickier, but our sliding window still handles it smoothly. Remember, we only update that maxim variable when we find a valid subarray, meaning a subarray of size k with all unique elements.
So if we never find one,
Maxim will just stay at its initial value of 0. It's like our algorithm is saying, hey, I looked everywhere, but I couldn't find what you were looking for.
okay, that makes sense. It's a good way to handle that situation.
What about the case where all the numbers in the array are negative?
This is an important one to consider, but guess what? Our sliding window algorithm can handle this too. It's designed to find the maximum sum whether the numbers are positive or negative.
So if all the numbers are negative,
It will find the subarray of length k with the smallest negative sum, which is technically the largest among all the negative ones.
so it still finds the best possible solution, even if it's not ideal.
Exactly.
Okay, so our sliding window solution can handle empty arrays, cases where k is too big, cases where there's no valid subarray, and even cases with all negative numbers.
It's a pretty robust solution. It is. Now, before we wrap things up, I'm curious, why is this maximum sum of distinct subarrays problem so popular in tech interviews?
That's a great question. It's popular because it tests a lot of important skills. It's not just about writing code to solve the problem. It's about problem solving, understanding algorithms, and thinking critically about efficiency.
So it's like a little mini project that shows the interviewer how you think.
Exactly. They want to see how you break down the problem, how you approach it, and whether you can come up with an efficient and elegant solution.
And, of course, they also want to see if you can communicate your thought process clearly.
Absolutely. Communication is key. Can you explain why you chose a particular approach, how it works, and why it's better than other options?
So it's really a test of your overall technical abilities.
And those skills are essential for any software engineer or data scientist.
Well said. So if anyone out there is preparing for technical interviews,
Definitely add this problem to your list.
it's a classic one,
Okay.
and it will teach you a lot about algorithms, data structures, and problem solving.
And remember, it's not about memorizing solutions. It's about understanding the concepts and being able to apply them to different situations.
Fantastic advice. I think we've covered a ton of ground today. We explored this problem from different angles, looked at solutions, discussed efficiency, and even tackled those edge cases.
It's been a great deep dive, and hopefully our listeners are feeling more confident about tackling these kinds of algorithmic challenges.
On that note, we'll wrap up this episode of AI Codecast. Until next time, happy coding.